This is the View Pre-Calculus course. We're doing topic 7, which is factoring trig expressions. So first thing, a quick reminder, way back when we did factoring as like topic 2, I gave you a factoring checklist. The 0 step is if it's an equation, which it won't be here because these are all expressions, but if it is an equation, make sure one side equals 0. And then we work through the list of GCF, binomial, quadratic trinomial, even number of terms to try grouping, and then finally synthetic division. Now, it's very, 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 very rare that any teacher or test is going to be so mean that they're going to give you a trig expression that you have to factor with synthetic division. So we can pretty much check off both synthetic division and the even number of terms and grouping. They're both very unlikely here. So sort of the bread and butter of this is really going to be the GCF, the binomial, and the quadratic trinomials, which we're going to work on. So let's start with example 1 and 2. So we're going to factor these fully. So the important thing to remember when dealing with trig functions is that the stuff inside the trig function is a package deal with the trig function. There's no such thing as just sine. It's sine of x. So that x, right, so this sine x is a package deal. This whole thing, sine x, is a package deal. So if you notice, there's a sine x in each of these terms, right? The first term is sine x times cosine x, and the second term is just a sine x. So there's a GCF here, and the GCF is that whole sine x package, right? And if I take that out, what's going to be left is going to be a cosine x, and then whatever was sitting in front of the sine, which is a minus 1. So I'm going to get a cosine x minus a 1. And again, the x is inside the cosine, the 1 is not, and that's my fully factored expression, right? So I have a GCF, and I have leftovers, and I am factored. It's really not awful, but again, it's important to remember that the stuff inside a trig function stays with the trig function. There's no such thing as just sine. You can't write sine. It's got to be sine of x, or sine of theta, or sine of something. All right, so let's do the same GCF trick with the second one. So again, we have two terms here, right? We have a sine squared x, which means a sine times another sine. And then we have a cosine cubed x, which means cosine, cosine, cosine. 3 of them. Cosine x, cosine x, cosine x in a row. And then plus 4 sine x times a cosine squared x, which means cosine x times cosine x. So it looks to me like the largest number of sine things that I can factor out, because this guy only has one sine and this guy has 2, is that I can take out one of the sine x's, right? And when I do that, I'm left with one of the signs here and then nothing, like no sign over here, right? So we'll go ahead and put that plus 4, and then there's no sign there. Okay, cool. And then it looks like for the cosines, the biggest thing I can take out, this guy has 2 cosines and this guy only has, and this guy has 3, so the largest number of them that I could take out would be a cosine squared of x, right? Which would mean that there's a single cosine left here and then nothing left here because I took out the whole thing. So my final answer ends up being that I have this GCF of sine x cosine squared x times a sine x cosine x plus a 4. And that's fully factored, okay? So we're going to start there. Now let's, so those are just GCFs. Now, one thing that can make trig stuff a little bit more confusing, and you'll see this when we get to example 3 right now, is that sometimes we can't factor expressions the way they're handed to us. When you learn trig in your class, you're going to spend a lot of time learning some useful trig identities. Trig identities are sort of like making change. If I told you that 4 quarters equals $1, you wouldn't think anything of it. You'd say, cool, 4 quarters equals $1, that's true. If I told you 12 inches equals a foot, you'd be like, yep, that sounds about right. So trig identities are sort of like that. They're like conversion factors that we can use. So I'm going to give you a couple of useful trig IDs that we're going to need to do some of these. And for right now, you're just going to have to trust me that they're facts, just like 4 quarters equals $1. So first one is, if I give you sine of 2 theta, that is identical to writing 2 sine of theta cosine theta. Again, you don't know enough really to prove this yet, but it's true. And the second one I'm going to give you actually has 3 possible options. The cosine of 2 theta can either be rewritten as cosine squared theta minus sine squared theta, or as a 2 cosine squared theta minus 1, or as a 1 minus 2 sine squared of theta. And actually, I will give you a third one in case it ends up mattering, and this one is a big one that comes up a lot. Sine squared theta plus cosine squared theta is a 1. So those trig identities come up a lot, especially number 1 and number 3. Number 3 probably comes up more than almost any other trig identity. So knowing that, we're now going to use that information to walk through example 3. So in example 3, we're asked to factor sine of 2x minus a root 3 times a cosine x. Well, here's the problem. there's obviously no GCF. There's no numbers in common. There's no trig functions in common. But the stuff inside the trig function isn't even the same. So I'm going to use this trig identity right here, this number 1, that sine of 2 theta is 2 sine theta cosine theta, to rewrite sine of 2x as 2 sine of x cosine of x. And then I'm going to have this minus root 3 cosine x right after it. Right? Well, now I suddenly see a GCF. I notice that both of these have a cosine x, right? There's a GCF of cosine x now. So I can factor out a cosine x, and when I do that, what's going to be left is a 2 sine of x minus a root 3. And that's my factored answer. So again, in order to do that, you have to know a trig identity, and I realize that this is a pre-calc crash course, so we don't spend as much time on things as you will in a regular pre-calc course, but that's the gist of how you do example 3. Cool. All right, so we will not need the trig identities for 4 or 5, so I'm going to erase them, and we're going to walk through examples 4 and 5, and then you'll do some practice problems. So example 4, in example 4, we are asked to factor 2 sine squared x plus 7 sine x plus 3. So the thing is that this can't actually be a quadratic trinomial because polynomials don't have trig functions. Polynomials have powers of x's, and these aren't powers of x's, these are powers of trig functions. But if we look at this term, the term that is not squared, the linear term, right, the one that's not squared, let's call that, I'm going to call that u just as a letter to pick. It doesn't have to be u, but I'm going to call it u. I think we can agree that that would make u squared a sine squared x. So let's say I use that substitution and say 2u squared plus 7u plus 3. Well, this is totally a quadratic trinomial. So when I look at these, I usually call them secret quadratic trinomials, and if I'm not very careful to enunciate, I sound a lot like Elmer Fudd, secret quadratic trinomials. So, in case you needed a Looney Tunes reference. So once I get here, I can say, wait a second, I know how to factor this. I know my front seats have to be a 2u and a u. My back seats have to be a 1 and a 3 with the same sign, and then this will tell me the sign. So I know that I have a 2u and a u, right? I know it's a 1 and a 3, and I know they both have plus signs, so it's really just a matter of where I put the 1 and the 3. Since I want a 7 here, if I put the 3 opposite the 2, I'll get a 6 plus 1. So then the last step to finish example 4 is to replace u with what u is. U is sine of x. So 2 sine of x plus a 1 times a sine of x plus a 3. And that's my final answer. Now, again, you don't have to necessarily do this. If you can look at this and say, wait a second, I see what's happening, that's a secret quadratic trinomial, then that's dope, and congratulations, and it's totally awesome. But if you can't see that, then this u substitution kind of helps. This is a different u substitution than the kind you're going to use in calculus to do integration. So, same idea though. It's literally called u substitution because you are substituting a thing with the letter u. All right, let's do an example 5, and then you can do some practice problems. So in example 5, we're going to do the one that we haven't done yet, right? If you look at my checklist, I told you that we were primarily going to use these 3 things. And sure enough, we did 2 problems with the GCF. We just did a quadratic trinomial. So we're about to look at a binomial. So in example 5, we're asked to fully factor 16x to the 4th, or sorry, not x to the 4th, come on brain, sine to the 4th of x minus a 1. So there is no GCF, right? There's no GCF. I've got a 16 and a 1, there's a sign, there's not a sign. It is a binomial, right? So I say to myself, well, could this be one of those difference of squares? And it looks to me like if I rewrite this as a 4 sine squared x, quantity squared minus a 1 squared, it is a difference of squares, where my a is 4 sine squared x and my b is a 1. So this is going to factor into a, 4 sine squared x plus b, right? So 4 sine squared x plus 1, and an a, 4 sine squared x minus b, which would be minus 1. So this thing is prime. We've seen this before. This is called a sum of squares. This is done. But this guy is another difference of squares, right? Because 4 sine squared x, that would make my a 2 sine of x, right? And my b would be a 1 squared. That's a 1 squared, so my b would be 1. So this thing factors into a 4 sine squared x plus 1 times a plus b would be 2 sine x plus 1. A minus b would be 2 sine x minus 1. And this crazy thing is what that's going to factor into. All right, so you have a handful of problems. I think it's 5 of them that you're going to give a try.